Welcome back to Very Ordinary Differential Equations. In this lecture, we continue studying higher order linear equations with constant coefficients, but we move on to the study of non-homogeneous equations. We begin with something known as the method of undetermined coefficients. Suppose we have an nth order linear differential equation in our standard form. We already know that if we want to find all possible solutions to this differential equation, all we have to do is find a fundamental set of solutions to the complementary equation, which just requires factoring the characteristic polynomial. Then we just need to find one particular solution to the original non-homogeneous equation. Well then, how are we going to find one particular solution? Let's suppose all the coefficients are constants. So now we have an nth order linear differential equation with constant coefficients, but we're no longer necessarily assuming it's homogeneous. We're going to use the same techniques we developed for second order equations. If the forcing function is a polynomial or an exponential function or trigonometric functions or some sort of combination of those things, the method of undetermined coefficients says, suppose that y sub p is the same basic type of function but with some unknown coefficients thrown in. Then try to solve for those coefficients. However, if some term is a solution to the complementary equation, then you multiply by powers of x until it isn't. And solving for those unknown coefficients is called the method of undetermined coefficients. So overall, it's pretty similar to how we did it with second order differential equations. The superposition principle still works for higher order differential equations, just as it did for second order equations. So if your forcing function is a sum or difference of various things, you can tackle them one by one. So whatever form each term of the forcing function takes will require a different setup for the method of undetermined coefficients. As a first example, let's just find one solution to this differential equation. Now pay attention to the forcing function. It's a polynomial, 2x squared minus 1, plus an exponential e to the x, and those are different sorts of things. So we're going to find a yp1, which in the differential equation will produce the polynomial 2x squared minus 1. Then we're going to find a yp2, which in the differential equation produces the exponential e to the x. By the superposition principle, the particular solution we're looking for will simply be the sum of those two things, yp1 plus yp2. Now 2x squared minus 1 is a polynomial of degree 2, so we're going to presume that yp1 is also a polynomial of degree 2 with undetermined coefficients, ax squared plus bx plus c. So if we presume that yp1 is a degree 2 polynomial with undetermined coefficients, we start computing derivatives, y prime, yp1 double prime, triple prime. So here are the first, second, and third derivatives of our degree 2 polynomial with undetermined coefficients. Now I take these terms that we've just computed, and we throw them into the differential equation on the left-hand side. 2 yp1 triple prime minus 3 yp1 double prime plus 2 yp1 prime minus yp1 simply gives me 0 minus 3 times 2a plus 2 times 2ax plus p minus ax squared plus bx plus c. That simplifies down to negative ax squared plus the quantity negative b plus 4a times x plus the quantity negative c minus 6a plus b. Our goal, however, was to produce the polynomial 2x squared minus 1. So we conclude that a must equal negative 2. That will give me a 2x squared here. And then between negative b plus 4a equals 0 and negative c minus 6a plus 2b equals negative 1, with the known value of a being minus 2, you can eventually solve that b is negative 8 and c is negative 5. Therefore, yp1 is ax squared plus bx plus c, or negative 2x squared minus 8x minus 5. We're not done, however. We need to find some yp2, which in the differential equation produces my exponential e to the x. However, before we go ahead and set up yp2 equals a e to the x and just try, we should verify that e to the x is not already a solution to the complementary equation. Now, it's not totally necessary to fully factor the characteristic polynomial 2r cubed minus 3r squared plus 2r minus 1 equals 0. Rather, you can just check, is 1 a root? And in this particular case, it is. R equals 1 is a root, meaning e to the x is actually a solution to the complementary equation. So instead of letting yp2 being a e to the x, we let it be ax e to the x. But we should actually check that x e to the x does not also solve the complementary equation. Now, to check that x e to the x doesn't solve the complementary equation, what we should verify is that r minus 1 squared cannot be factored out of the characteristic polynomial. Now, here is the characteristic polynomial, and we already know we can factor an r minus 1 out of it. And when you do, what's left behind is 2r squared minus r plus 1. That quadratic does not have r minus 1 as a factor because 1 is not a root of it. Meaning, while r minus 1 could be factored out of the characteristic polynomial, r minus 1 squared cannot be. Therefore, e to the x does solve the complementary equation, but x e to the x does not. So we're going to let yp2 be an unknown constant a times x e to the x. So we're testing yp2 being an unknown a times x e to the x. We compute its first, second, and third derivatives. Then we throw those into the differential equation and simplify. Altogether, with yp2 being ax e to the x, 2yp triple prime minus 3yp double prime plus 2yp prime minus yp results in 2a e to the x. And we were simply trying to get out an e to the x. Therefore, if we let a equal 1/2, we're good. So altogether, yp2 is 1/2 x e to the x. So we have now found a suitable choice for both yp1 and yp2. So all we have to do, remember by the superposition principle, is add them together. For yp1, we had negative 2x squared minus 8x minus 5, and for yp2, 1/2 x e to the x. So here is one particular solution to the differential equation as stated in the problem. As our second example, let's find a general solution to y triple prime minus 4y double prime plus 10y prime minus 12y equals 4 times the sine of 2x. Well, we can begin by solving the complementary equation, which we do by factoring the characteristic polynomial. R cubed minus 4r squared plus 10r minus 12 is 0. After some work, we have a single linear term and one irreducible quadratic. So the general solution y sub c to the complementary equation is given by some constant e to the 2x plus some other constant e to the 1x sine or cosine of root 5x. So here we have our general solution to the complementary equation. Now we turn our attention to finding one solution to the original non-homogeneous equation. Now sine of 2x did not show up in the fundamental set of solutions to the complementary equation. So we can start by setting y sub p being some constant times cosine 2x plus some constant times sine of 2x. Remember from our work in second order differential equations that when you're trying to produce a sine or a cosine, you generally need to assume you began with both. Now with this choice of yp, we take a derivative and we take a second derivative. The reason we needed to start with both is that when I start adding and subtracting them against one another, we will get sines and cosines. We also need a third derivative, so we go ahead and compute that. Throwing all of these into the differential equation will eventually simplify down to 12b plus 4a cosine of 2x plus negative 12a plus 4b sine of 2x. So with this yp, a cosine 2x plus b sine of 2x as our choice for the function that we're hoping will solve our differential equation, when we plugged it into our differential equation, this is what we got. So with yp as a cosine 2x plus b sine of 2x, we ended up with this once we threw it into the differential equation. We wanted to only produce 4 sine of 2x. Therefore, the coefficient on the cosine of 2x should be 0, while the coefficient on the sine of 2x should be 4. 12b plus 4a is 0. Negative 12a plus 4b is 4. This is just two equations and two unknowns. We quickly are able to solve it using any technique you want, really. A is negative 3/10, b is 1/10. Therefore, y sub p is negative 3/10 times the cosine of 2x plus 1/10 times the sine of 2x. So we found a general solution to the complementary equation and one particular solution to the non-homogeneous equation, which means the general solution to the differential equation as given in this example is the particular solution plus the general solution to the complementary equation, or -3/10 cosine 2x plus 1/10 sine of 2x plus some constant e to the 2x plus another constant e to the x cosine of root 5x plus a third constant e to the x sine of root 5x. As a third example, let's solve an initial value problem. We've got a fourth order linear differential equation with constant coefficients, and we're given y of 0, y prime of 0, y double prime of 0, and y triple prime of 0. So to solve an initial value problem, we need to come up with a general solution to the differential equation before we can even use those initial values. To find a general solution, as we saw in the previous example, we need one particular solution, but we also need a general solution to the complementary equation, so we're going to start there. Now the characteristic polynomial, you can eventually factor as r plus 5 to the fourth. Therefore, a fundamental set of solutions to the complementary equation is e to the minus 5x, x squared, and x cubed times e to the minus 5x. So now, since we were trying to get out e to the minus x, which is definitely not going to be a solution to the complementary equation, we can just let y sub p be a e to the minus x. We're going to take this y sub p and throw it into the differential equation and hope to get out 1792 e to the minus x. So we compute its first, second, third, and fourth derivative. Since we just have an e to the minus x, thankfully this is pretty easy. Then we take these and put them into the original differential equation, which simplifies down to 256a e to the minus x. And we were trying to get out 1792 e to the minus x. That just means a is 7. Therefore, y sub p is 7 e to the minus x. So we have a fundamental set of solutions to the complementary homogeneous equation and one particular solution to the original non-homogeneous equation. So the general solution can be given by the one particular solution we found plus an arbitrary linear combination of elements of our fundamental set. Now we can start using our initial values to determine what these unknown constants C1, C2, C3, C4 are. So y of 0 is 10. If I go ahead and plug 0 in here, x cubed, x squared, x all vanish, and we get 7 plus c1 equals y of 0, which was 10. Therefore, c1 is simply equal to 3. Well, now I can go ahead and replace that c1 is 3. So we determined that c1 is 3, which means we can write our solution like this, but now let's compute a derivative. It takes a bit of time, but if I differentiate every term in y, after some simplification, you'll end up with this. And now we can use the knowledge that y prime of 0 is 0. If I go ahead and plug 0 in for x, both of these vanish, both of these vanish. However, here, notice we get a c2 times 1 e to the 0. Here we'll get a 15 e to the 0 and a negative 7 e to the 0. Altogether, y prime of 0 is 0, so here's a 0 on the left. And what did we get from all of this? Negative 7 plus 15 plus c2, which we can quickly solve for c2 is minus 8. So we're going to take this value of c2 and put it into y. So y we have now solved for c1 and c2. Therefore, y prime is as given here. We're just taking the y prime that we computed here and substituting that c2 is now known to be negative 8. So here are y and y prime. Now we can compute y double prime. After some work and some simplification, there it is. Now we can use our initial value that y double prime of 0 is 0. So on the left we'll get 0, and on the right we're plugging in x equals 0. So anywhere you see an x remaining here, it's going to vanish, but e to the 0 is 1. Altogether, what do you get? 7 plus 75 minus 80 plus 2 times c3. Therefore, c3 must equal minus 1. So we take that value of C3, put it into y, and also put it into y double prime. We don't really need to put it into y prime. It's kind of irrelevant at this point. At the end of the day, we do want our function y, so we're going ahead and doing that. But since we did have y double prime, we can now take y triple prime. After a bunch of simplification, you should get all of this. We take our initial value, that y triple prime of 0 is 2, which gives us 2 is negative 7 plus 375 minus 600 minus 30 plus 6 C4. That allows us to solve for C4 is 44. And now finally, we can take that value of C4, throw it into the function y, and get 7e to the minus x plus 3e to the 5x minus 8x e to the 5x minus x squared e to the 5x plus 44x cubed e to the 5x. In summary, what did we discuss? The method of undetermined coefficients works for higher order equations in much the same way it did for second order equations. However, more and more derivatives have to be computed to use it properly, so it starts to become a lot of work the higher order equations you're working with.